protocol. Okay, can you tell me what are the different type of protocol we have? Based on the communication protocol and based on the peripheral protocols, we have different type of protocols, right? Communication protocols are nothing but we have like high speed protocol and low speed protocol. High speed protocols or USB, PCIe, ethernet, these protocols works under high speed. Okay, whereas a low speed protocols nothing but I2C. Okay, I2C or SPI, these protocols works under low speed. High speed, low speed is nothing but in terms of bandwidth. Okay, so the USB or PCIe, these are like high level. High level in the sense these works under high speed communications. Whatever our laptops we are using now, present days laptops or mobile phones, not mobile phones, mostly laptops. In laptops, we will use the USB port and PCIe port. Previously, in olden days, what we have used UART port or USART port we have used. There are a lot of disadvantages by using the yacht and the USART like that. That's why we have moved to the USB. Okay, then PCI. PCI is one of the most high speed protocol which can be used for data transfer in between the device. Okay, like from RAM module to our processor. If you see, there is like a big bus, 32-bit bus. If you see, there will be wire in old motherboards. If you see in old motherboards, there will be like a big wire in the size 32-bit wires. If you see, that is nothing but PCIe cable. Okay, so like that low speed protocols are nothing but I2C or SPI. And not only communication, we have the peripheral bus protocols. These protocols works under serial communication. Serial communication means all the data will be sent serially, one by one bit. Okay, whereas bus protocols are nothing but there are AMBA protocols. You have the idea. Suppose in our SOC there will be lot of IPs will be there. Okay, if you want to connect with the one IP to another IP, we will use one bus here. Okay, very big bandwidth bus. That means a high speed bus. Okay, so it will be in the size of 64 bit or 128 bit like that. Those protocols are nothing but the bus protocols we can call. Okay, very high speed like APB. APB is the less speed compared to the AHB AXI. Okay, APB AHB AXI we will discuss in the coming sessions. So present today we are discussing the communication protocol, which is a low speed protocol I2C. Okay, so I don't know whether you have the idea or not. We have discussed previously what are the different classification of protocol, like based on the way of data transfer, way of direction of transfer, based on synchronization, like that. Okay, so if you miss those sessions, you can go through the sessions in YouTube. Those are available in semi design. So coming to the I2C, so what is mean by I2C? Where we will use the I2C protocol practically. Okay, whatever the system we are seeing, whatever the motherboards we are using in our computers, where we can use this I2C. Okay, so we'll discuss now. First of all, I2C is nothing but we can also call I square C. Okay, so I2C is nothing but inter-integrated circuit. Inter-integrated circuit. Okay, it is invented by the Philips. You know the Philips company, right? The semiconductor company. So it is invented by Philips and also NXP semiconductor in 19th century, like 1980s, around that time, at 1989 think so. So it is a multiple master multiple slave. What is the master and what is the slave? Suppose what is mean by protocol? It is a communication. That means we will follow some rules. Okay, what are the rules we need to follow? Suppose this master I am considering as a processor. There will be cores within the processor. Okay, this is slave I am considering as a north bridge IO or any graphic processor or any memory module. Okay, I am considering this slave as a memory module. Okay, so if you want to transfer the data from this to this, what the rules you need to follow? Okay, mainly what is the size of the processor and what is the memory of the processor. Okay, suppose it accepts 128 bit, means how much size it will accept, either 64 bit or 128 bit. That size you need to observe first of all. Then what is the communication process, either it is a serial communication or parallel communication. That is the one point you need to take. And is it a half duplex or full duplex? Mostly protocols will be half duplex only. Half duplex means write and read operations cannot done at a time. Okay, if write operation is done at particular time, after completing of that, then only we can perform the read operation. So write and read operation cannot be done at a time. These are the rules you need to understand. Okay, and what is the next rule, like whether it is a synchronization or asynchronization? What are the protocols, asynchronous protocols we have? UART. UART is the asynchronous protocol. In this, we didn't used any clock, right? Based on the baud rate, we have generated the UART. But coming protocols, baud rate is not good for synchronization. We cannot provide the more synchronization between the transmitter and receiver. That's why we're using the clock. So here we need to check the clock also according to your address and data. Okay, so these all the rules we need to follow. And what is the distance between a source and a destination, or a master or a slave, or a transmitter or receiver? These all the names we can call. Okay, and what is the bandwidth? The processor is working under which bandwidth, and what is the memory bandwidth? Okay, these all things we need to note. And based on that, which protocol is can be used. Okay, processor to memory means it is in inter, that mean intra communication. Okay, we have two types of communication. Okay, inter system communication and intra system communication. What is a inter system? Suppose this is our computer motherboard. Okay, if you communicate the motherboard with the outside of the microcontroller. Okay, suppose this is your laptop, this is your mobile phone, you are connecting through the USB cable. Okay, so to our laptop, mobile is communicating, that means outside the device is communicating, so it is inter system communication. Okay, inter system communication, what are those protocols, like USB or UART or USART? By using that port only you will communicate, right? Like that we have intra system communication. Okay, what is mean by intra-system? Suppose this is the motherboard. Within the motherboard, suppose the processor or some any other IP, some IPs to IP, or within the IP to some other blocks, we will communicate, right? That communication is nothing but intra-system communication within the circuit, the block to block communication. Okay, those communication can be done using I2C protocol or SPI protocol. Okay, two types of protocols we have on intra communication. So I2C, SPI, both are similar only. Okay, so and coming to I2C, it is a intra-board communication and it is a half duplex communication. It is a synchronization communication and it is also serial communication. The data can be transmitted serially, and it is a short distance communication. Short distance means within the circuit board, very short distance between the block to block. We can communicate block to block. It is a short distance and it is very low speed. If you observe PCIe, I2C, in place of I2C, present as we are using PCIe, which is one of the most high speed protocol, very high bandwidth protocol. Okay, so PCIe is replacing the I2C in some of the components, not for all. Okay, because some components will work on the low speed and some will work on the high speed, right? So it is the low speed, maybe 100 kbps, 100 kb per second. Okay, to or greater than 100 kbps. Okay, so this is the main I2C. I think you got the clarity what is meant by I2C protocol and somewhat protocol information, right? Have any doubts up to here? Have any doubts up to here? Okay. Next, coming to the introduction, whatever we have discussed, those things, it is a synchronous, it is a multi-master and multi-slave. Multi-master, multi-slave means nothing but multiple masters can be used and multiple slaves can be used. Okay, multiple transmitters, multiple receivers, or multiple source, multiple destinations we can call. Okay, it is a packet switched. You know what is mean by packets? Nothing but number of bits can be transmitted in a packet wise, and single ended, we'll discuss that. And so it is invented by Philips Semiconductor, and it is a short distance, it is a low speed peripheral. Okay, and mainly see, I2C has a bidirectional signals mainly. Okay, what are those bidirectional signals? It has a SDA serial data and SCL serial clock. Okay, SDA as SCL serial data and serial clock. Based on these two signals, everything will be happen, like whether transmission should happen, or address to be sent to the slave, or data to be sent to the slave. Okay, all the things will be happen through the SDA and the SCA. Okay, suppose if you remember UART protocol. Okay, in UART protocol, what are the things are there? Based on the there will be a frame format for address data, first start bit, address data, parity bit, stop bit, right? That is the frame format for UART protocol. Like that I2C, I2C has some frame format. Okay, and in yacht, how we have designed, there is a transmitter block, receiver block, baud rate block. Like that we have designed the yacht. Like that I2C has some other specification, like APB has some other specification, AHB has some other specification. So by using different type of protocol, we are able to send the data from the transmitter to the receiver. That means one block to another block. Okay, I think you are getting the point. So how the master is connected to the slave, like this. In master we have the SDA SCL signal. Not only SDA SCL, we'll have data, address, acknowledgement bits, everything will be sent like this. Okay, and this theory part you can go through that. I will share you the screen, like a PDF. Okay, now coming to the I2C frame format. By using this frame format only, we are going to design the I2C protocol. Okay, this is the main important thing. Whoever asks the interview questions, they will ask mainly what is meant by I2C. So whatever we have discussed the specification, you can tell those things, and you have to explain this frame format. And if you go to advanced level, they will ask some more interview questions like arbitration, clock stretching concepts. These are the main things in the I2C. Okay, so now we'll see the frame format of the I2C. So what is the frame format? SDA, SCL. Two signals are there. If you see here, SDA is high to low. Okay, and SCL is high, constant. So whenever the condition meet here, SDA must be high to low and SCL must be high. Okay, in this condition, in this condition the data is nothing but start. Okay, it is the start condition, representing the start condition. Okay, in what is the representation of start condition? Like the start bit should be 1. What is the representation of stop condition? The data should be 0. The data should be 0, but that is not more synchronization. It doesn't have more synchronization. So here, with respect to the clock and with respect to data, we are taking this condition for the start. If you see here, at last, the SDA should be low to high and SCL must be high. This is nothing but stop condition. Whenever the signal reaches to this, it will automatically stop. Okay, stop condition. Next, in middle, what happened? Whenever we it reached like this, whenever we find it this one, it able to start the data. Okay, once the start condition gets started, the master able to send the address to the slave. Okay, so master is sending address to the slave. What is the main thing, master? that is transmitter, it will send address to the slave to the particular address. In that particular address it should store some data. That is the main thing. Master, what is the slave? Slave is nothing but it responded to the master. Whatever the master sending the signal, it the slave will respond to the master, right? So here slave will respond to the master according to that. If slave receives correct data, or if slave doesn't receive the correct data, or if slave is not able to receive the data, okay, it will send the acknowledgement and not acknowledgement to the master. Acknowledgement, not acknowledgement means just like information, okay, it is sharing whether it is able to receive correct data or not, like that. Okay, so if you see here, what is the address? Actually address is a 8 bit, okay, up to here A0 to A6 is the address, but first bit is there, right? Here or W. What is that or W? Or W is nothing but either read or write transformation. Okay, so if it is in read operation, it should not perform the write. If it is in write operation, it should not perform the read. Okay, based on that, they will the system, whatever the code we are design engineers are writing, so we will write that thing. Okay, and acknowledgement, if you see here, ack is nothing but acknowledgement. Who is sending that acknowledgement? For the master, the slave is sending the acknowledgement. Why the slave is sending the acknowledgement? Because this address already sent from master to slave here, right? If that slave is receiving that address correctly, it can send that acknowledgement, okay, I have received the data correctly, or I have received the address correctly. Okay, if that particular address is not available in the slave, then it will send the not acknowledgement. This particular address is not available, like that it will send some not acknowledgement. Okay, or something as data has filled already in that particular address, so slave will send the not acknowledgement signal if it is not ready to take that particular one. Then if slave send acknowledgements, acknowledgement means master again initiate the new transfer. Okay, so that is the address and acknowledgement. Next one, if you see, data. Once address sent, next data. What is the data here? It is a 8-bit data. Okay, it is the 8-bit data. Master will be sent to the slave and receiving the acknowledgement if particular data received correctly or not. It will send again acknowledgement signal. If acknowledgement is true, that means it received the correct data. If it send not acknowledgement, means somewhat error is there. We need to find out that error. Okay, so again, stop condition. Once the data is received, here stop condition. Okay, so this is not only from master to slave. If you want to send from slave to master also, same format we need to use. First start condition, address to that particular address the data have to send. Again stop condition. Okay, so did you understood everyone the frame format of I2C protocol?
Ma'am, here SCL, what its functions do, what
SCL
it
is nothing
represents.
but SCL is a clock. It is a clock, serial clock. Normally we will generate the clock, right? So that is nothing but a clock. Suppose this is the clock. And SDA is some data. SDA is some signal, whatever. This address, what are these addresses? Nothing but 011011, some like that only, right? Binary format. So this is nothing but overall data or address or read, right? Or acknowledgement. Everything in terms of binary only, right? So suppose SDA is like this here. Suppose here A6 I am taking 0, A5 I am taking 0, A4 1, A3 0, A2 1, A1 0, A0, and again I want to do the write operation. Again I want to take some data. So what is this? This is nothing but data, SDA. So but for start operation we are checking for this condition. Okay, like this here.
Okay, ma'am.
Okay, have clarity, everyone?
Yes, ma'am.
Okay, so this is the frame format of I2C protocol, and these are the things whatever I have discussed now. So what is the start condition and what is the stop condition? Middle, it is sending some data and sending the address. Okay, so these are the timing diagrams. What is the timing diagram here? For the I2C protocol, sometimes they will ask the timing diagram also, okay, in interview. Then what you need to do mainly means just you need to write the start condition and you need to write the stop condition, and middle how the addresses, how the data are transmitting, just those things you need to mention. Okay, see here, start condition, here address, b6 to b0 or by W, write or read or write, acknowledgement and data and acknowledgement, stop condition. Very simple to understand and we can remember easily. Okay, for every protocol we'll have start, stop condition, middle, address or data. Very simple to remember. Okay, but coding wise not that much of simple. We need to write by understanding clearly. Next, these are the applications where we can use the I2C. Common applications of I2C bus, describing the connecting cables via ROM configuration, plug and play operations like accessing real-time clocks or some chips, RAM chips, accessing low-speed digital to analog converter, analog to digital converter, controlling LCD displays like that. Whatever the low-speed operations are there, some of the digital operations in the circuit, there not only in the laptops, we will see multiple wherever the digital circuits we are using in our alarms or remote controller, gaming, so many are coming, right? So those uses very less bandwidth. If you see remote controller gaming things, those use very less bandwidth, so like those type of things we can use. Okay, so this is the I2C protocol. Did you got the clarity everyone, specification wise? We will see how to write the coding now, like how to develop the finite state mission for this particular frame format, we'll see. Okay, have any doubts here?
No, ma'am.
Okay. Okay, so what is the main thing, what is the main thing we have to write in the finite state mission? You already know what is mean by master. What is the master? Can anyone tell? What is the slave? Can anyone tell? So master is nothing but who will initiate the transfer and generate the control signals to the transfer. And slave is nothing but it responds to the master. And it is a I2C is a two-wide communication. One is the serial data SDA. One is the serial clock SCL. Okay. So mainly how to write the final state mission. Suppose if you see the slave, okay, slave or master, suppose if you see final state mission for the slave, first what is the main final state mission we need to write? It is the main thing we need to write in the final state mission. What is the first state?
Ideal state.
Ideal state, initial state. So what is happening in the initial state here?
If it receives some data from master, then it goes for next state. Else it
Yes.
remains in the same state.
Yes, very good. So ideal state, initial state is nothing but first it will go to start signal which is generated by the master. right? Suppose when SDA is go from high to low, check here. When SDA is goes from high to low, SCL is high, serial clock is high. Like that, if same go to the next state, like say slave will sample and it will become to the ideal state to the start state, right? Suppose it is in the start state. Ideal state means it is a zero condition. So from zero condition to the, it will go to the start state. Start state is nothing but SDA and SCL conditions we need to check. Okay, so we will check those things in the ideal state. Okay, I'm just telling theory wise. When we write the code, how we will write the code, these things we can check. Okay, so ideal is nothing but it is checking for the conditions of SDA and SCL. Okay, next one, start. What is the start state? We need to write the condition of SDA and SCL. Okay, we need to write the condition of SDA and SCL. Okay, can you tell me what is the next state? After start condition, what is the next state? Address, right? Address. So here, what address? Slave address. What we have to do in the address state? Slave address state, actually master will send the slave address, right? From the master, it will initiate to transfer the slave address to the slave. Okay, then slave will check the address which must be same. Okay, the slave address and whatever the master has generated, that must be same. Okay, if it is same, it will go to the next state. If it is not same, it will go to ideal state, right? So if same, next state, not same, ideal state. Okay, now what is the next state? What is the next state?
If it is same, it need to send an acknowledgement. No?
Yes, very good. If it is same, it should send the acknowledgement to the master, then only master can understand, right? So slave acknowledgement will be generated by the slave, right? Because slave have to slave will generate acknowledgement. Okay, so after generating, how it will send to the master, with whatever the address match, it will send to the master, right? So that means either 0 or 1, everything we will understand in terms of 0 or 1. Okay, so 0 means acknowledgement received correctly, so it will go to next state, or otherwise you can design like a 1. Okay, that all depends on the user things. Okay, so here 0 means next state, 1 means it will go to the start state again, because it will transfer from the start state, because acknowledgement is not correct. Okay, that means slave is not received the data properly. If acknowledgement is not correct, again master have to initialize the transfer. That's why it will go to the ideal state if acknowledgement is not correct. Okay, next, what is the state?
Stop state.
Stop state. No, here actually we send the like slave address. Next one is a register address. Okay, next one is the register address. So what will be done in the register address? 8-bit address. Total we have 8-bit address. If you see here, total 8-bit address. In that 8-bit address, or by w, that means read or write operation is happening. Okay, so in this what we need to write means, we will take total this as a register address. In that 8-bit address, 7-bit will be the actual address and 1 bit will be the write or read signal. 1 bit will be the write or read signal is generated by the master. Okay, so it will convert the parallel data to the serial data. Okay, and the data will be sent to the slave. Actually, here we don't know what is this master. This master may come the data parallelly. Okay, that master is connecting some other block. Okay, suppose here there are two blocks. This is one block. This data master, here it is sending some parallel data to this master, but this master cannot send the parallel data to the slave because it is a I2C protocol, right? That's why this master have to convert this parallel data serially to the slave. Without converting, we cannot do the operation. So for that converting purpose, what we are doing, we have to use the parallel to serial converter shift registers we have, right? So that thing we have to do here. Okay, so the data will be converted parallel to the serial and send the data to the slave. So slave will connect again to the parallel. Slave will store the address. Okay, why slave have to send parallel data? Suppose here master and slave is there. We don't know again the slave which for which master it will connect. Maybe it will connect to the serial master or a parallel master. We don't know those things, right? Again, we have to convert to the parallel data for transmitting to other master. Okay, here we will connect some other protocols like a APB protocol, bus protocol. So the slave will convert that parallel data, and through the APB bus protocol we will send again to the another master, that means another IP or another block. Okay, so in between this is the I2C protocol, which is a serial communication. Did you understood? So register address is nothing but it will whatever the register total address is the 7-bit address, it will divide into 7-bit and plus 1 bit. Okay, and that it will transmit parallel to the serial and serial to the parallel converter. Okay, so after register address there will be register acknowledgement also. Register acknowledgement, what is that register acknowledgement? It is generated by the slave. Okay, see, what is the register acknowledgement? The register acknowledgement is generated by the slave, right? So if address is present in the slave, it will generate the acknowledgement as a 0. Other, otherwise, it will send acknowledgement as a 1. Acknowledgement, not acknowledgement, we will call as a not acknowledgement. NACK. Acknowledgement, not acknowledgement. Okay. And what is the next state? Next state will be the write operation, either read operation. So how can you check whether write operation or read operation? In the register address state only, we need to write either write operation or read operation. We need to select that thing. Okay. So here next state will be the write or read operation. Here suppose it is equal to 1, then we can call it as a read operation. If it is a 0, then we can call as a write operation. Okay, so either write operation or read operation, based on that we will go for the next state. Suppose it is a write operation, what is the next state? Write data. What is the next state? Write data. So what we will do in the write data? Whatever the 8-bit data generated by the master, master will convert that parallel data to serial. So send the data to the slave. Right, again slave will convert the serial data to the parallel data. The slave will store the data in that particular address. That is the main thing. Right, the right address. That is the main thing for the right data. After writing the data, what will get? Write data acknowledgement, right? So you understood write data, right? If you don't understand, please let me know, I can explain again. Okay, next one is write data acknowledgement. Same whatever I have shown in the frame format, I am writing in terms of finite state mission. So if you write like this, when you are doing the coding, you will get easily. Okay, you can write the code easily. Okay, so next state is the write data acknowledgement. What will be done here? So whatever generated by the slave, if the slave receive the data properly, it will generate the acknowledgement 0. Else it will generate the not acknowledgement. Okay, so if slave generate the acknowledgement, what happens? Write transfer is completed. If it is not if it is not generated, that means if it generate not acknowledgement, the write transfer is not completed. Again, it will go to the ideal state, or otherwise it will go to the register address state. Okay, so the transfer is completed. If you want another transfer, again you go to start state. Suppose if you want to transmit 32-bit data, sometimes 32-bit data means 4 times we need to do the 8 bits, right? Suppose I2C is limited with the 8-bit data. By using the I2C, we can send the data only 8-bit. Suppose, but your input data is 32-bit data. So if you want to send 32-bit data, what happened? 4 loops. You need to take 4 loops. Okay, once the transfer completed, again, like that 4 times you need to take. Okay. And next, acknowledgement has completed. Next, what is next state? Read state. What is the next state? Read data. So what happens in the read data? Can anyone? You are giving very late reply, so I am only telling. Can you tell anyone what is the read data? Read data is nothing but 8-bit. It is the 8-bit data will be generated by the slave, right? The slave will convert the parallel data to the serial data. So that serial data again will be transferred to the next master. Okay, the master again will convert to the parallel data to the serial data to the parallel data. Suppose if it want to convert any parallel communication. Okay, so that is nothing but read data which can be sent by the slave. Okay, after the read data, we will get the acknowledgement. Read data, acknowledgement. You already understood, I think so, what is meant by acknowledgement, right? So 8-bit data which is generated by the slave, whether it is generated properly or not, received properly or not, that will be sent through the acknowledgement and the not acknowledgement, so that here the read transfer is completed. So if you want get another transfer, you need to go for start state again. Okay, if you want another transfer, if you take 32-bit data, like that. So if you don't want any other transfer, you can go to the stop state. You can go to the stop state. What is the stop state? Here we have the stop. Before going to the stop state, go for stop wait state, because it is waiting for the stop. Okay, waiting for the stop means what? Here we need to satisfy the condition. Okay, so slave will wait for any stop signal generated by the master. If stop is generated, it will go to the stop state. Else remaining in the it will remains in the stop state only. Okay, stop wait state only. So next state is the stop state. Here we need to generate stop wait completed. That means we are waiting for the stop signal. In the main stop, we will write the condition. What is the SDA and what is the SCL? That condition we will write. So whenever SDA is a positive edge, that means low to high, right? The condition. Whenever SCL is high, that will be the stop condition. So low to high, SCL is high. That is the stop condition. So in the stop, we will check the we will check that condition. Once that condition satisfied, it will go to the stop state. Okay, did you understood everyone up to here?
Yes, ma'am.
Okay, so here we are telling I2C is a bidirectional. I2C is a bidirectional. So bidirectional means two signals we need to select, right? Either SDA or something SDA out. If you store in the temporary, so those things we'll discuss in the coding when we discuss. Tomorrow we'll discuss the coding. So that time you can observe the clearly. And next, another thing, main important questions we'll discuss now. So in I2C, one of the main important interview question is clock stretching. What is mean by clock stretching? And what is mean by Suppose there are multiple masters. Okay, here there are four number of masters, there are four number of slaves. So I want to store the data in one slave or second slave, whatever, but I'm not able to select the master from which master I want to send the data. So how can I select the master? There are four masters equally transmit the data. I can send through any one of the master, but which master I need to select as a data transfer? This is the main question. So here comes the arbitration concept. Okay, suppose here we have two signals. If you have two masters, this is very easy to solve. We have two SDA SCL. So what is the start condition? Can you tell me? This is very logical question. Which master can send the data if two masters are there, three masters are there? SDA clock is reduced. No, no. For SCL, one master is selected that which satisfies the initial condition. Which satisfies the initial condition means, can you elaborate that thing? Can anyone? For which means SDA is low. Yes. Okay, good. What is your name? Charan. Okay, good. So I didn't got more clarity what you said, but you reached the thing. See, three masters will generate SDA and SCL. Right, this master will also will generate SDA and SCL, and this master also will generate SDA and SCL, and this master also will generate SDA and SCL. But we cannot tell all the masters will get SDA SCL condition at a time. Okay, all masters will not satisfy the condition at a time, right? So that is a random generation, right? So maybe second master will generate first, or first master will generate second time, or like that. So whoever master generate first, that condition satisfies the first master, that master initiates the transfer. Okay, so this is nothing but arbitration concept. Okay, this is one simple example, or we can also take the arbitration concept by using the AND gate. Okay, if there are multiple number of masters, we can use the AND gate concept when we are dealing with the program. I will tell you how to write with the AND gate arbitration concept. Okay, next concept is clock stretching. What is mean by clock stretching? Clock stretching is nothing but, here master will operate at some frequencies and slave will operate at some frequency. Suppose master is operating at high frequency. Master is working at a high frequency and slave is working at a operating at a low frequency, like this. So if master and slave have different frequency, how the synchronization will happen? No synchronization will happen, right? So there will be some of the situations where I2C will not able to cooperate with the clock speed of the master. So here we will need the clock down. Okay, so here the master have to do the clock down. Okay, so this mechanism we are calling as a clock stretching. This mechanism we are calling as a clock stretching. So how can we write this clock stretching in terms of coding? Means if the slave is not ready, it will make the serial clock low, because this clock is running at high speed. Here the slave is not ready to that particular high speed. So it will make SCL low. So SCL equal to clock stretch 1 bit binary 0 SCL. If clock stretch is high, it will go to 0, making constant, otherwise SCL. Will get the data of serial clock. Okay. Or clock stretching and edge triggering both same. Clock stretching means it is a frequencies. Edge triggering is different. All are edge triggering only, right? All the clocks we are using edge trigger only. But clock stretching means we are making the clock to make it low frequency. Okay, clocking down for stabilizing more. Okay, here master is working at high frequency. We are trying to stabilize the master. That means improving the delay. We can tell as improving the delay, which can be equal to the slave clock. Okay. So this is the today's session. I think hope you got what is mean by I2C protocol and how to write with respect to the finite state mission. So if you have time, you can develop this finite state mission I2C protocol, or otherwise you can create your own finite state mission using this frame format. Okay, and you can try to write the Verilog programming. Okay, tomorrow we'll discuss the Verilog program anyhow, how to write the for the frame format. Okay, have any doubts in this session? Anyone have any doubts? Okay, then thank you. Thank you for joining. Okay, I'm closing the session. Did you have any doubts in writing the final state mission? Okay, we'll quickly recap the things or whatever we have seen the I2C protocol in the last session. Okay. You have doubted read operation. Okay, we'll see. Coming to the finite state mission, how we have written the finite state mission based upon the form. There is a frame format, right? So what is there in frame format? There is a SDA signal, SCL signal, data, and a clock. There is a start condition for the data. What is the start condition for the data? Can anyone tell? High to low for SDA, and for clock it should be high, constantly high. So this is the start condition. If you go for yacht, what is the start? Just one bit start bit means then it will be start transferring the data like that stop. But here in I2C we have SDA and the SCL signals. Okay, so what is the stop condition? SDA must be low to high and SCL must be constantly high. This is the stop condition. So whenever it receives like this, it should stop the transferring the data. Okay, so based on that, here we will have 8-bit address. In the 8-bit address, only 7-bit is considering, 1 bit is read or write data, and there is a acknowledgement. Why the acknowledgement? Whether the receiver received the correct data or not, correct address or not. If it not receive the correct address, it will send the not acknowledgement signal. So master will transfer, initiate the transfer, again. So once address is confirmed, if it is send the acknowledgement signal that it received the correctly, then it will go to the next state, that is nothing but data. So here total 8-bit data will be there, and also after sending the data there will be an acknowledgement signal. Okay, we'll get either not acknowledgement, acknowledgement. If acknowledgement we got, it will, next state will be the stop, wait, stop condition. If we got not acknowledgement, that means the data receiving, whatever the receiving data has some error. Okay, if any error data has received, it will give the not acknowledgement. Then again it will have to initiate the transfer, so it will go to the ideal state. So this is the frame format. Based on the frame format, we have to write the final state mission. Okay, same thing you can follow for UART also. In UART also we have start condition, address, data, parity bit, stop condition, like that you can write the states. But in UART we have written in the transmitter block, receiver block, baud generator, like that, right? So this is the different one. Like that, next tomorrow if you see APB, it has some different format, like it has some final state mission, and it has the waveforms, like that. Okay, so this is the I2C protocol. We'll revise the final state mission once again. Okay, so see here, what is the ideal state? First, it will go to start signal, which is generated by the master. That is the main ideal. So we need to check the condition here. When SDA is go to high to low, and SCL is must be high, constantly high. Then slave will sample, and ideal data will be start. It will go to the start state, from ideal to the start. Okay, so in the start state we'll have this logic and slave address. After start we'll have the slave address, right? So master will send the slave address, slave will check the address which must be same. If same, it will go to the next state. Otherwise, if it is not same, it will go to the ideal state, like that. Like next slave acknowledgement we need to check. So it is generated by the slave. If address is matched with the master, it will send the acknowledgement. That means correct, it will go to next state. If it is correct, not correct, it will go to the start state. Like that, register address, 8-bit address we have taken, right? In that 8-bit, 7-bit is the address, 1 bit is the write or read operation. Based on that write or read operation, either 0 or 1, it will initiate the transfer. Okay, either read operation or write operation. So it is generated by the master, and it will convert to the parallel to serial and send the data to the slave. Again, slave will receive serial to, it will convert serial to parallel to send to the next master, as we discussed. So, and again register acknowledgement. Whatever slave receive the address, whether it is received correctly or not, the slave have to send the acknowledgement signal to the master. If it is receiving correctly, it will send the acknowledgement is equal to 0. Then it will go to the next state. Next state is nothing but write or read. Based on the write or read bit, whatever you are giving, based on that it will go to either write state or it will go to read state. Okay, suppose here write or read equal to 1, directly it will go to read state. Otherwise, if it is equal to 0, it will directly go to write operation. Suppose here it is a 0. Okay, then it go to the write data. What is the write data? First, master have to generate the 8-bit data, then it have to convert the parallel data, whatever it is coming from other slave. Before slave, the parallel data, if it come, it will convert the parallel to serial data. Then the master will initiate the transfer. Serial data will be transferred from the master to the slave, as I will show. Suppose this is the master, from other slave, master is getting some parallel data, then this master have to convert that parallel data and send to the slave serially. And again, slave will receive the data. If it want to send some other master again, it should convert that serial data to the parallel data, because for every master to slave middle we have the interfaces, right? A block to block we will have interfaces. Those interfaces are nothing but a APB protocol. If you take a low bandwidth, if you take high bandwidth, those are AHP, AXI. So nothing but those are the bus protocol. For that purpose, we need to convert into the parallel. Okay. Next, so send the data to the slave. Slave will convert that thing, and write data acknowledgement. So if write data received by the slave, correctly, it will send to the acknowledgement as 0, write transfer completed. If you want to transfer other write data, what we have to do? Suppose if there are 32-bit data, total 32-bit data is there, we need to take 4 number of transactions. Okay, first one time 8 bit, after completion of one 8 bit, then second, then third, then fourth, like that. Okay, 4 times we have to initiate the transfer. So if you don't want another transfer, you can directly go to the stop condition, stop state. If it generate not acknowledgement, again you have to go for stop or start state. Either ideal state you can go, or you can stop the transferring that transaction. Okay, if it is not write operation, if it is a read operation, suppose slave have to do the read operation, means then write read equal to 1, directly it will come to the read data. Okay, what here it is reading, doing 8-bit data will be generated by the slave is the reading the data here. Okay, slave will be generated the 8-bit data, and slave will convert that parallel data to serial data, and serial data will be transferred. Okay, so master will convert again serial to parallel if slave want to send another transaction, otherwise slave will store that read data. Okay, and read data acknowledgement, so it is generated by the master. If master receiver data properly, master will send acknowledgement 0, else it will send acknowledgement 1 when slave is transferring to the another master. Okay, so if retransfer is completed, if no transfers are there, it will go to the stop state, otherwise it will go to the start state and not acknowledgement. And next one is stop wait state. What is the stop wait state? Without going directly to the stop state, we are just checking here whether it should go for stop or not. Okay, so slave will wait for any stop signal generated by master. Okay, stop signal means SDA must be low to high, low to high, and SCL must be high. That condition, if stop is generated, it will go to the stop state, as else remaining in the wait state only. Why it is remaining in the wait state only? Because it is waiting for the any transmissions or happening in between. Okay, if any transmissions happening in between, it cannot go directly to the stop state. That's why we need to put stop wait. Once the transmissions are completed, then only we will go to the stop state. Up to that time, we have to wait for the stop. Once waiting completed, it will go to the stop state. Okay, so if master generates any start signal, it will go to start, or it will be in stop only, in the stop state. When will be the stop state? It will be positive edge of the clock, that means low to high, and SCL must be high. So this condition we will check mostly. Okay, so this is the main finite state mission we are going to generate for the I2C protocol. Okay, so we have discussed the bidirectional signal. What is the bidirectional signal? Here we have SDA and SCL, both two are bidirectional signals, right? So for the SDA data input, we are making directional enable. Suppose if directional enable is 0, it will go to high impedance state. If it is 1, the SDA output will be sent to the SDA main signal. So directional enable, in each state it will tell the what is the direction. Okay, suppose if it is master to slave, then directional enable is 1. If it is slave to master, we need to transfer, then directional enable equal to 0. Okay, this is how every time we have to check for both directions, either to master to slave or slave to master. Okay, else in the stop condition, when this condition satisfy, it will go to the stop. Okay, and main two important questions in the I2C protocol is clock stretching. What is the clock stretching? As we discussed in the previous class, when there are high frequency, master will operate at the high frequencies mostly, right? So when it is operating at high frequency, slave will operate at the low frequency. Wait, this is not. So these are the high frequencies we have, and slave will operate at the low frequency. So in this case, what happened? The slave cannot be cooperate with the master clock. This is the very high speed it is operating, but slave is operating at very low speed. Mean there is a mismatch. The communication mismatch is there. Master will transmit the transfer very quickly, but slave is not acceptable, not able to accept the transfers very quickly. But both should have the synchronization, right? Either slave have to run fast, or either master have to slow down. We need to make the constant of the master, right? So that's why we are making here clock stretching. Clock stretching is nothing but we are making the clock down here for some time to match with the slave. Suppose here clock is 2 cycles. Within the one slave cycle, here clock or 3 4 cycles. So if you make clock down making sometime constant, then we can able to match with the slave. Both the clock frequencies we can match, right? So that's why here we are using the clock stretching concepts. Okay, so here there are some situations where I2C slave will not able to cooperate with the clock speed given by the master, so it needs a clock down. That's why we are using the clock stretching here. Okay, so how we will use practically that clock stretching means, see here, if slave is not ready to receive the data. Okay, when master is giving the data quickly, master is giving very fastly the data, but slave is not able to receive the data. Slave is not run with the master. Okay, so we have to make a SCL as a low. Okay, see here, SCL clock stretch. When clock stretch is high, 0, clock stretch is 0, SCL. Okay, so like that we can make a constant by keeping the constant. Otherwise, SCL equal to SCL. We are assigning the actual clock to the clock. Otherwise, it is 0, making the constant value. Okay, so this is the clock stretching concept. You can explain for the interviewers like this. Okay, mostly. And next one is arbitration concept. We already discussed the arbitration in the last class. What is the arbitration? Suppose there are the multiple masters are there. Master 1, master 2 are there, master 3 are there. So which master can transfer first? We need to select any one of the master. Okay, if there are multiple masters also, by using one master only we can initiate the transfer. But how can we initiate the transfer, or internally how the system will initiate which master will be selected? Can you tell me? In last session we have discussed. Can you tell me that which coincidence with initial conditions? What are the initial conditions we have? What are the initial conditions we have? Yes, clock of SCL. Uh, Yeah, SCL and SDA. Suppose SCL should be constant and SDA must be low to high or high to low. Okay, we cannot tell for all three masters will be high to low at a time, right? Maybe at this master, this high to low, this condition satisfy at 10 time units. Okay, and for this master the condition will be satisfied at 20 time units. For this master the condition may satisfy at 50 time units, like that. So if any master work with less time, so this master will automatically start the start condition. These two are being hold, right? That's how we can select the master. Or otherwise we have the arbitration concept. Okay, we'll discuss the arbitration concept. So if there are multiple masters, what can we do? Here we are using the arbitration concept by using the AND gate or NAND gate. Okay, we can use any gate. So if you see here, there is a master 1. Master 1 sending the address 11010, suppose. And master 2 sending the address 10101. And master 3 sending the address 10110. Okay, so we need to perform the NAND operation or AND operation. Okay, suppose if we perform the AND operation here, what happens? Suppose um 3 1 into 1 into 1. What is the output? Output is 1, right? Here 1 into 0 into 0. What is the output? Output is 0. Okay, so if you see here, 1 is not equal to 0 and these both are same with the given output. Okay, what is the remaining thing? What is the remain one? Which is nothing but this one, master 1. Remaining two are same with the output, right? So here master 1 will lose the bus. Okay, so it cannot do the operation, it cannot initiate the transfer. Automatically master 1 will do the will lose the bus, so we don't have this data. Okay, next master 1 and master both these two, here master 2 and master 3, 1 into 1. What is the output? 1 into 1 means 1. So here both are same, both are same means in this condition we cannot check. Both masters will not lose the bus. Okay, next one, 0 1. 0 1 means what is the output? 0 into 1 is nothing but 0. See, 0 means here which is same to the master 2. Okay, output is same to the master 2 and this one is different, so here master 3 will lose the bus. Okay, remaining which one is there? Only m2. M2 will on the bus and it will start the transfer. Okay, so this is the clock stretching and different arbitration concept. Okay, arbitration is nothing but when there are the multiple number of masters, how can be achieved? Which master can initiate the transfer? Okay, that is the main thing. I think you all understood the concept wise I2C protocol, right? Have any doubts? Have any doubts? Clock should be one for clock stretch. Um, Clock should be one for clock stretch. Means you mean here we have taken the clock based on the clock stretch. We have taken suppose there are the inputs for the clock stretch. Okay, based on that we will consider this one bit binary 0. Otherwise, that mean it has high frequency. Clock stretch in the sense a high frequency. So if it is a high frequency, we are making constant by putting the 0. Okay, and if it is not in high frequency, whatever the SCL clock is there, SCL is nothing but main clock. Whatever the clock we are generating, that is the main clock. Okay, so that SCL will be assigned to the actual SCL. Here this SCL is the temporary. Okay, we'll see the coding, then you can understand how you will write the clock stretching. Okay, so up to here you don't have the doubts, right? Anyone? Okay, okay. See here how to write the system verilog verification plan and test bench. We'll see now. Okay, see. This is the slave, I2C slave module, I2C slave. These are the signals we have: reset, SCL, SDA, data out, and address out. Top level signals. Okay, so input is the reset, address is the 7-bit, data output is the 8-bit. SCL and SDA are the bidirectional signals. That's why we are taking as a in out signal. Okay, And these are the temporary variables. What are the temporary variables? We have write, read data. This is the wire. And address in write data, read data. These all are temporary serial input, parallel output. We need to convert, right? When we are sending master to slave, slave to master. And piso, parallel input, serial output. And count for counting 8-bit data or 8-bit address. And present state, next state. When we are writing the final state machine, both are needed. And SDA out. What is the SDA out? The serial data output, a temporary variable. Then we will send to the actual output. Next, direction enable. You have seen directional enable, right? And we are creating the memory. Okay. And if you see here, these are the write enable, read enable, start, stop, count enable, CPO enable, PSO enable. These are the enable signals and the valid signals. Okay, to initiate anything, first we will make the enable signals, right? So those things. Next, parameter, ideal state, start state, whatever the states we have seen here. Okay, what is the first state? We have ideal state, slave start, slave address, slave acknowledgement, register, write data. Same thing we have written here. Okay, ideal state, start, register address, acknowledgement, write acknowledgement, read acknowledgement, stop, and stop wait. So these are the conditions we have. So what are the conditions? Directional enable we have seen, right? So SDA equal to directional enable, SDA out 1 bit Z, and data output equal to read out. Directional enable 1 equal to means write equal to 1. uh, yeah, directional enable 1 means master to slave, and direction enable 0 means slave to master, right? That is how we are making here SDA output. If direction enable 1 means SDA output, whatever the temporary variable we are storing, that will be sent to the main SDA. Otherwise it will be the Z. Okay, and read data is the temporary variable we are sending to the output, main output. And address out, write data. What is this? Total we have one address input, 8-bit address input, right? But in that 8-bit address input, how we are dividing? First 0 to 7, 0 to 6 are out address, and 1 bit is the write. So here we have taken the conditions. Okay, and next